We are laying the groundwork for a network designed for instantaneous global connectivity. 6G must handle massive sub-terahertz data streams, frequencies capable of transmitting gigabytes of information in a fraction of a second. But developers are hitting the computation wall. Standard processors cannot calculate the incoming data fast enough to maintain these 6G frequencies. Pushing this volume of data through traditional x86 and ARM architectures causes processors to generate immense heat and introduces critical signal latency. The current bottleneck is a physical limit in how our chips process data. Our existing architectures have reached the end of their capacity to manage this level of throughput. The root of this failure lies at the microscopic level, in the basic way computer addition was designed decades ago. This is the standard integer limit. Traditional arithmetic logic processes numbers sequentially. It reads bits in a straight line, one after another. When an equation requires you to carry a 1 to the next column, the processor must pass that bit down the chain, step by step. This is carry propagation. As we increase bit widths for 6G networking, that linear chain becomes too long. The time it takes for that carry to travel the length of the string creates a massive computational traffic jam. Our telecommunications infrastructure is currently restricted by this linear sequence. Standard logic cannot force data through a straight line fast enough for the 6G era. In 2004, an engineering project began exploring a different path. It looked past the standard sequential logic of the time to address the integer limit. The project proposed a complete departure from traditional design, solving the bottleneck by removing the straight line from the equation. This led to the Vishwarupa Multidimensional Framework, or VMF, a structural approach that changes the physical geometry of data. VMF stops treating numbers as flat strings. Instead, it maps them as symmetrical, multidimensional blocks. Using a center-outward method, the processor calculates the block from its central symmetry point in all directions simultaneously. This bypasses the sequential carry chain entirely. By organizing data into 3D geometry, VMF removes the need for bits to wait in a linear queue, clearing the path for high-speed throughput. This multidimensional logic scales through the 2 to the k framework, a mathematical structure that mirrors how complex systems organize in the natural world. Research into primordials and number theory suggests that natural systems utilize symmetrical patterns to process information with the lowest possible energy expenditure. VMF intentionally aligns the computer's arithmetic logic unit directly with these primordial structures. This allows the hardware to process complex transcendental mathematics using a fraction of the clock cycles required by a standard processor. To reach the next level of processing power, we are moving away from man-made linear constraints and adopting the symmetrical efficiency found in mathematical theory. Applying this symmetrical ALU to our 6G infrastructure provides the technical bypass needed to overcome the computation wall. The data shows the impact. VMF accelerates essential signal processing, such as FFT and IFFT, by over 70%. This speed facilitates ultra-fast frequency hopping at nanosecond scales, allowing the network to maintain stable connections at sub-terahertz frequencies. Crucially, VMF utilizes symmetrical heat diffusion. This spreads the thermal load evenly across the architecture, reducing dynamic power consumption by 21 times compared to linear chips. By resolving the thermal and sequential bottlenecks simultaneously, the VMF framework clears the primary technical hurdles that have stalled 6G development. The VMF's symmetrical ALU is now a formal filing with the Indian Patent Office, moving from theoretical research into a hardware solution for global connectivity. This journey from a 2004 student project to a patent-holding architecture reflects the Atma Nirbhar Bharat ethos of indigenous, self-reliant technological innovation. The infrastructure of the future depends on a solution that began with a quiet, 2-decade-long exploration of prime numbers and mathematical symmetry. We can overcome the most complex challenges in modern telecommunications by returning to the fundamental efficiency of geometry.